Have you ever noticed a question? Why does the universe have rules and constraints? Logically, randomness and chaos should be the more natural state. Yet we live in a world governed by order at every turn, from the movement of electrons to the rotation of galaxies, from the speed limit of light to the minimum Planck length. Everything seems to obey an invisible cosmic code. The question is, who set these rules? Were they always there, or were they deliberately designed? But knowing what the rules are isn't enough. The real challenge is understanding why they work. So next we'll follow this doubt, peeling back the layers of the cosmos step by step, to see whether order truly governs everything, or if chaos is the real master behind the scenes. And to find the answer, we must start from the most fundamental and most mysterious point of departure, the principle of invariance. You can drop a ball in New York, or conduct the same experiment on the moon. The result will be the same. It bounces in an identical way. That's because the fundamental laws of physics are independent of location. They remain consistent no matter where you are, from the tip of your pen to the heart of a distant galaxy. This property, unchanging across place or time, is called the principle of invariance. It means reality is not a chaotic patchwork of random phenomena in different places, but a complex and coherent unified structure. This consistency exists because there is no privileged position or special moment in the universe. Whether you move an experiment elsewhere, change its orientation, or run it at a different time, the outcome stays exactly the same. Whether you measure an electron's charge, a photon's energy, or the gravitational pull on a falling apple, the underlying equations are always the same set. It is this symmetry that forms the basis of cosmic uniformity. More importantly, the power of invariance lies not just in the mathematical consistency, but in its guarantee that physical laws must hold everywhere. Otherwise, the universe would become a random monster. Galaxies might form in one place while disintegrating in another, and the patterns we use to orient ourselves in the cosmos would be completely scrambled. In fact, we verify invariance every day by repeating experiments in different locations. In particle accelerators, we smash protons at tremendous energies, and no matter where the accelerator is built, the interaction behavior is identical. If someday a detector in Europe failed to detect a certain particle, while one in Japan succeeded, it would signal a fundamental problem. But that's not the case. Every experimental station, every telescope, every instrument produces consistent results. This tells us we live in a universe governed by unified laws. Even Einstein's theory of relativity is built almost entirely on invariance. He insisted that physical laws, including the constant speed of light, must be the same for all observers regardless of their motion. This principle sparked a scientific revolution. Simultaneity was overturned, space and time merged into a dynamic whole, and gravity was redefined as geometry. All because physics remains unchanged under motion. Invariance is also directly linked to the conservation laws we rely on. Energy is conserved because physical laws don't change over time. Momentum is conserved because physical laws don't depend on position. Soon, Emmy Noether will mathematically explain this connection. Invariance also explains why science is universal. Astronomers, chemists, and engineers can build telescopes to probe the depths of the early universe, and the patterns and phenomena they discover follow the same physics that powers your phone's battery. Without invariance, we'd have no reason to trust observations from the James Webb Space Telescope or Mars rovers. Thus, invariance means our physical models aren't just local snapshots. They are genuinely universal truths. Yet how far does this invariance extend? Does it hold everywhere for all time? We're not entirely sure. Perhaps it breaks down in the early moments of the Big Bang, or under extreme conditions of quantum gravity. But until such cracks are found, it remains the strongest glue holding reality together. Maybe one day we'll discover that nature's ultimate invariance is not absolute, only approximate or even breakable. Until then, Every precise test supports its existence. This isn't luck, it's more like a signal that nature seems built to be understood and transmitted consistently. This leads to an important conclusion. If physics is constant, the concept of location loses meaning. It means even if you and an alien from billions of light years away are separated by vast stretches of space-time, you can both measure gravity, electrons, and photons the same way and get identical results. Even if their tools have different names, their DNA and society are utterly alien, their atoms still obey the same rules as yours. It is this cosmic consistency that gives science its meaning. In other words, we're not just collecting odd phenomena from here and there, we're searching for a universal language. The universe isn't a collection of isolated islands, each with different physical rules. It's a unified whole governed by the same laws. So why does physics always work? Because the foundation of the world is built on invariance. It means no experimental direction or error can alter how nature operates. That's why we trust that stars shine the same way across space-time, electrons carry the same charge everywhere, and conclusions about the tiniest particles studied on Earth apply equally to the edge of the observable universe. Moreover, symmetry in nature is the blueprint hidden behind the laws. Imagine rotating snowflake. Whether you turn it 60 degrees or not at all, looks the same. That's symmetry. An object remains unchanged under certain transformations. In physics, symmetry isn't just about beautiful shapes. It's the key linking all measured forces, equations, and particle interactions. In fact, symmetry is so important. It's sometimes called the language of natural law, or the secret code that makes everything from electrons to galaxies make sense. In physics, symmetry refers to a system remaining unchanged under a transformation, moving a particle's position, rotating it, mirroring it, or even swapping matter and antimatter. If the equations describing the system remain valid after such a change, the system possesses that symmetry. Why is that remarkable? Because each symmetry corresponds to a conserved quantity, something that remains constant no matter how the system evolves. If physical laws don't change over time, energy is conserved. If they don't change in space, momentum is conserved. If they're invariant under rotation, angular momentum is conserved. This deep connection between symmetry and conservation isn't coincidence. It's a rigorous mathematical truth, which we'll explore in the next part with Noter. Similarly, forces arise from symmetry. Electricity works because how we handle electric charge follows a specific symmetry. Likewise, the strong and weak nuclear forces stem from more abstract internal symmetries. These can't be visualized as simple rotations or mirrors. They exist in mathematical spaces, where quantum properties like charge, flavor, or color can vary. As long as the equations hold, symmetry remains. But when the balance is broken, things get interesting. In fact, much of our world structure comes from broken symmetry. In the early universe, all forces may have been unified into one perfectly symmetric whole. As the cosmos cooled, this unity fractured, giving rise to the separate forces we know today. It's like heating a perfect snowflake. Its petals melt away, leaving a new, stable but asymmetric form. Particles like electrons and quarks gain mass through such spontaneous symmetry breaking. Initially, the Higgs field that gives them mass was balanced, but that balance was later broken. Once symmetry breaks, particles interact with the Higgs field, and mass emerges. Symmetry isn't limited to particle physics or the early universe. It's everywhere. In chemistry, molecular shapes often obey symmetry rules. In biology, butterfly wings, zebra stripes, and animal patterns are shaped by symmetric developmental processes. Even in economics, some models rely on behavioral and probabilistic symmetries. Nature seems to start with symmetry, deviating only when it gains something: structure, mass, or diversity. In mathematics, symmetry is closely tied to group theory, a branch of algebra studying transformations. Every known fundamental force in physics can be described by a symmetry group. The standard model of particle physics is built on these principles, using groups like SU3, SU2, and U1. Don't worry about the symbols. Just know these groups describe how particles behave, how they interact, and what changes they can undergo without breaking physical rules. The more we learn about the cosmos, the more it seems symmetry isn't just a useful tool. It may be the hidden scaffold reality is built on. If you were to design a stable, predictable universe, full of emergent phenomena from scratch, the most sensible approach might be to start with symmetry rules. But not all symmetries exist. Why is electric charge conserved, but parity not conserved in weak interactions? Why do particles obey some mirror flips but ignore others? Nature seems to pick and choose symmetries, sometimes even deliberately breaking them, as if following an unknown script, balancing elegance and complexity. This raises a bigger scientific question. Could physical laws themselves arise from a deeper, more perfect symmetry? Perhaps the universe we see today, with all its flaws and asymmetries, is just the shattered remnant of a more perfectly symmetric reality, like a once complete statue now cracked and weathered by time. And this is precisely what Noether's theorem addresses. Where do the laws in mathematics come from? You may have heard, for every action, there's an equal and opposite reaction. But what if I told you, nature has a conservation rule for every symmetry, not just logically but as a strict mathematical fact? That's what Noether's theorem is all about. It's one of the most important ideas in theoretical physics, from German mathematician Emmy Noether. Her insight quietly changed how we understand the world. In the early 20th century, Einstein had just proposed general relativity, redefining gravity as the geometry of space-time. But a problem soon arose. When trying to apply traditional conservation laws like energy conservation to Einstein's new framework, things got fuzzy. In curved, dynamic space-time, physicists struggled to even define what energy meant. That's when Noether stepped in. In 1915, she proved something astonishing. Every symmetry in a physical system corresponds to a conserved quantity. This wasn't just a useful observation, it was a rigorous mathematical law. For example, if physical laws don't change over time, time translation symmetry, energy is conserved. They don't change with position. Space translation symmetry, momentum is conserved. If they're invariant under rotation, rotational symmetry, angular momentum is conserved, and the deeper you go, the more it holds. Electric charge conservation is directly tied to the symmetry of electromagnetic field equations. Even more complex symmetries, like gauge transformations or internal quantum numbers, give rise to conservation laws, as long as they're continuous and differentiable. What makes Noether's theorem special isn't just listing physics rules, it explains their origin and necessity. Before her, scientists knew some quantities stayed constant, but no one could fundamentally say why. After her, we understood. Conservation laws are the result of symmetries. You don't even need to start by writing conservation rules. Just assume nature doesn't care about certain transformations, and conservation emerges automatically. Think of designing a physics engine for a video game. You don't need to code energy conservation separately. Just ensure the engine doesn't calculate physics differently from 1 second to the next, and energy conservation naturally follows. The same goes for space and velocity. Rules are written automatically by symmetry. This isn't just convenient, it's foundational. In quantum field theory, which underlies the Standard Model, Noether's theorem is central. Each fundamental interaction has a symmetry group, U1 for electromagnetism, SU2 for weak interactions, SU3 for strong interactions. These aren't just mathematical tricks, they determine how particles and interactions exist. Noether's insight even influences modern cosmology. Inflation theory, which proposes the early universe expanded faster than light, relies on the idea that vacuum symmetry can break, releasing energy and shaping space-time structure. You could say Noether's mark is found in nearly every corner of modern physics. Now, if every symmetry corresponds to a conservation law, what happens when symmetry breaks? That's where things get even more interesting. In physics, spontaneous symmetry breaking occurs when a system's fundamental laws are symmetric, but its actual solutions no longer reflect that symmetry. Imagine a pencil balanced perfectly on its tip. The laws are symmetric, but once it falls, it picks a specific direction, breaking the symmetry. And whenever symmetry breaks, something new is born. The Higgs mechanism, which gives particles mass, comes from symmetry breaking. Particle diversity, atom formation, even cosmic structure can be traced back to moments when perfect symmetry gave way to complexity. As for Emmy Noether herself, she faced immense prejudice in her time. Brilliant, yet for years she couldn't teach under her own name, and some important works had to be published anonymously. Nevertheless, her contributions are now considered among the greatest achievements in physics history, even called by Einstein a monument of mathematical thought. Speaking of another cornerstone of modern physics, gauge fields, the invisible structures governing all forces. On the surface, our world is made of planets, particles, atoms, and stars. But peel back the layers and you'll find a different picture. Fields that exist in space yet can't be directly seen. These fields control all the forces you feel. Gravity pulling you to the ground, magnetism turning compass needles, electricity powering machines. Behind them are gauge fields, not just background but the hidden scaffolding of reality, a mathematical structure dictating how particles move, how forces arise, and why the universe stays orderly. A gauge field is defined by symmetry, not symmetry of shape but symmetry of rules. Think of designing a game where players can choose any color outfit without affecting the outcome. That freedom to choose color without changing results is a kind of gauge symmetry. In physics, this means you can freely change a field state at every point in space, and the physical outcome remains unchanged. To preserve this freedom, nature's laws must introduce a corresponding gauge field. Electromagnetism is the best known example. In quantum electrodynamics, the electromagnetic force arises from AU1 gauge symmetry, a way to let quantum fields rotate freely. When you make this symmetry local, each point in space can rotate its field independently. A photon must appear. Yes, the electromagnetic field behind light, Wi-Fi, and lightning doesn't exist inherently. It emerges from mathematical balance. This holds for all fundamental interactions in the Standard Model. Weak interactions from SU2 gauge symmetry, strong interactions from SU3. These aren't just abstract terms. Each describes how a field varies and how particles respond. Force-carrying particles, like W and Z bosons, gluons, photons, are essentially symmetry's messengers. In other words, forces don't exist out of thin air. They're enforced by symmetry through fields. What's truly powerful about gauge theory is that it not only describes forces but predicts them. Once you choose a symmetry group, particle types and interactions emerge naturally from the math. Mathematics itself writes the universe. For example, to describe the strong interaction binding quarks and protons, just write an SU3 gauge field into the Lagrangian. You'll get 8 gluons and a complex dance of color charges. These equations don't just live in empty space, they shape space itself. In some quantum gravity theories, space-time may even emerge from gauge interactions. In string theory, gauge fields are fundamental. Tiny strings vibrate not only in position but in gauge space. In loop quantum gravity, the loops weaving space-time are outlined by gauge connections. In short, geometry and force structure may not be separate. They might be the same thing viewed from different angles. Gauge symmetry tells us physical laws don't care about arbitrary choices. You can change reference frames, rotate a field, tweak a parameter. The math still holds. But to keep the math consistent, nature demands compensation. And that compensation is the gauge field. It's like tuning a piano. You can choose a new reference pitch for each note, but to keep the music harmonious, you must adjust intervals. In physics, those adjustments are force fields, existing to maintain symmetry's harmony. Sometimes gauge fields interact with themselves. For example, the strong interaction involves gluons with their own color charge, so quarks can never be isolated. The harder you pull them apart, the stronger the force. In contrast, electromagnetic fields don't bind to themselves, so positive and negative charges can be separated. Each force's personality is shaped by its underlying gauge group. As for the Higgs field, it may itself be a gauge field. Its role sounds simple, giving particles mass, yet it reshaped all of particle physics. Without it, W and Z bosons would be massless, and the weak force wouldn't be weak as we know it. In fact, every time you feel gravity, electromagnetism, or nuclear forces, you're interacting with gauge fields. Every rule in nature, from how particles spin to how they scatter, is governed by this invisible network woven from symmetry. But a bigger question remains: why exactly these gauge fields? Why SU3, SU2, and U1? Why does the universe need these structures and not others? Physicists are still searching. Some think the symmetry might be larger, like SU5 or SO10, only broken into what we observe today. Others, from string theory, propose gauge groups emerge from extra-dimensional geometry. Some even guess gauge symmetry might just be a low-energy approximation of something deeper. Next comes another fundamental concept: Planck units, nature's built-in measurement system. The meters, seconds, and kilograms we use daily are human inventions based on arbitrary references. Like a silver rod in France or Earth's rotation, they're useful for communication, but they don't belong to the universe itself. So if we strip away all human definitions, keeping only the universe's native language, what remains? That's what Planck units are. In 1899, Max Planck proposed a measurement system, completely free from human convention, based only on nature's fundamental constants: the speed of light c, Planck's constant h, and the gravitational constant g. These constants are the universe's native code. When we measure in Planck units, we're not asking how many meters, but how big is this compared to reality's smallest possible structure? For example, the Planck length is about \1.6 times 10 carat minus 35 meters. Incredibly tiny. A proton is 100 million times larger. It's not just a short length. It's the scale where space starts losing smooth meaning. At smaller scales, quantum effects may tear and blur space-time, even dissolve it entirely. Many theories suggest the Planck length is where smooth space-time collapses into quantum foam. Correspondingly, Planck time is about \5.44 times 10 carat minus 44 seconds. The smallest meaningful time scale in physics. Shorter than that, sequence loses definition. Time may become chunky, jittery, or non-existent. Planck mass, on the other hand, is huge for particle physics, about 22 micrograms. This scale matters in quantum gravity, marking where gravitational effects can't be ignored and where a particle might become a tiny black hole. These constants aren't just technical details, they're the fundamental parameters setting the stage for everything in the cosmos. Combine H, C, and G and you don't get weird math. You get nature's operating system. Unlike meters or pounds, Planck units mean the same everywhere. If an alien civilization built physics from scratch, they wouldn't use inches or feet, but they'd know the Planck length, because it doesn't depend on their planet, language, or biology, only on how the universe works. Some physicists even see Planck units as reality's underlying code. Like a video game with a minimum pixel size and frame rate, the universe may have a fundamental resolution, and the Planck scale defines it. Anything smaller or faster might not be supported by the system. Yet here lies a deeper mystery. Why do these constants have the values they do? Why is the speed of light about 300 million meters per second? Why is Planck's constant so small? If any of these numbers changed even slightly, the universe would look completely different. Atoms wouldn't be stable, stars wouldn't form, life wouldn't arise. Yet they are exactly as they are. Planck units don't explain why the constants have these values. They just show how to combine them into a natural, intrinsic scale. In a way, Planck units are beautifully elegant, pointing to a universe indifferent to human preference, a universe describable in true or false terms. But they also raise unsettling questions. Are these constants truly fundamental, or are they just placeholders? Rough guides to a grander concept we've yet to fully grasp? Some scientists think known constants like C, H, and G might arise from something deeper, low-energy manifestations of a more fundamental structure. Their values might change at higher energies, or in other regions of the cosmos. If so, even the powerful Planck system is just a regional dialect in physics' broader native tongue. An even bolder idea: reality might not be physical, but digital. If so, Planck units represent the smallest information pixels, the indivisible units of space, time, and mass. Then physics would be like a program running on a cosmic computer, and the Planck scale would be its grid spacing. This aligns with quantum gravity, loop quantum gravity, and even simulation hypotheses. In other words, when we ask what the universe's natural units are, we're really asking, what are the underlying settings of this everything operating system? Planck units are like physics default settings, the universe's safe mode. Understanding them might be the key to rewriting reality's source code. Yet for all their elegance, they remain nearly invisible. No experiment has directly probed the Planck scale, because the energy required is far beyond our reach. Only extreme environments like black holes or the Big Bang truly touch these boundaries. Now let's turn to another mystery. Why is there a speed limit? The origin of the speed of light. A cosmic speed limit is set in stone, unalterable. In vacuum, nothing travels faster than light. About 299,792,458 meters per second, just over 300,000 kilometers per second. No matter how powerful your rocket, how much energy you pump into a particle, or how wild your idea, this limit cannot be broken. And this limit isn't just for light, it's the ultimate speed cap for everything in the universe. So why does it exist? To understand, we must rethink speed. In Newtonian mechanics, speed is simply space divided by time. Simple, intuitive, and theoretically unlimited. Want to go faster? Just push harder. But Einstein's 1905 special relativity shattered that myth. He showed space and time aren't separate concepts. They're two parts of the same fabric, space-time. And space-time has its own rules. As an object approaches light speed, its motion slows asymptotically toward that limit, mass increases, and the energy needed for even a tiny speed boost skyrockets. At 99.9999% light speed, extra energy hardly increases velocity, just makes the object heavier. Light speed is like a wall in space-time. No massive particle can cross it. Why? Because the speed of light isn't just a speed. It's the proportionality constant defining cosmic geometry. In special relativity equations, it links space and time, like a conversion rate between meters and seconds. If space-time is the stage for physics, light speed is part of the stage's framework. Light itself isn't the cause of the limit, it just happens to travel at this maximum speed. Photons reach this limit because they're massless. No mass, no inertia, so they naturally move at top speed. If massless particles didn't exist, we might not even know there was a speed limit. Light is simply the most observable messenger. So the key point isn't that light is special, it's that space-time's geometry dictates massless things must move at this speed. It's not light's choice, it's the universe's property. This connects to James Clerk Maxwell's 1860s electromagnetic theory. While organizing electromagnetic equations, Maxwell found a strange result. They predicted electromagnetic waves always travel at a fixed speed. Plugging in known constants gave a value, exactly the speed of light. Light, it turned out, is an electromagnetic wave. Not some mystical glow, but oscillating electric and magnetic fields in vacuum. These fields' behavior is controlled by two fundamental constants: vacuum permittivity and permeability. Combine them and you get C. In other words, C isn't an independent speed. It's the necessary result of how electromagnetic fields propagate in vacuum. Change electromagnetism's rules and you change C, but then space-time structure and all dependent laws would collapse. A new question arises. Why this particular number? Why not 1,000 kilometers per second or a billion km/s, but roughly 300,000 kilometers per second? No one really knows. If we use different units, the number would change. But in natural units like Planck units, C equals 1, showing it's not an arbitrary number, but a built-in scale in the universe's code. Some theories link C directly to causality. If information could travel faster than light, paradoxes could arise, messages from the future, effects preceding causes, time order breaking down. Special relativity, by setting C as the limit, preserves causality and keeps time stable. Bolder ideas suggest light speed might have been different. In the early universe, maybe even faster. Such variable speed of light theories have been proposed to explain cosmic puzzles, like why the distant universe looks so uniform. Usually, inflation theory explains this, but a higher early light speed might also solve it. However, no solid experimental evidence exists yet. Others wonder if light speed is truly the ultimate limit. Maybe gravitational waves or unknown interactions go faster. But so far, all evidence from particle physics, astronomy, and gravitational wave observations agrees. C is the ceiling. For us, this means interstellar travel will never be as easy as sci-fi suggests. No world drives, no hiperspacellamos. Unless we find loopholes like wormholes or quantum tunneling. Until then, light speed is the unbreakable limit. Next, we face another puzzle: standard model parameters. Who set these cosmic knobs? Imagine a dense control panel, covered in dials, each precisely tuned to a specific setting. These knobs control everything, from how electrons orbit nuclei, to how quarks bind inside protons. They set fundamental force strengths, particle masses, mixing, decay modes. Oddly, these knobs really exist, and they all belong to particle physics standard model. The standard model is our most successful framework for the subatomic world so far. It covers 3 of the 4 known fundamental forces: electromagnetism, strong nuclear force, and weak nuclear force. It includes all known elementary particles: quarks, leptons, bosons. For half a century, it has withstood countless experimental tests. Yet it has at least 19 free parameters, values that must be plugged in by hand, not derived from deeper theory. They seem independent, yet together they keep the cosmos running. Examples: 6 different quark masses, from the very light-up quark to the top quark heavier than a gold atom. Lepton masses, electron, muon, tau, and their neutrinos. Why these values? We don't know. Coupling constants, strengths of strong, weak, and electromagnetic interactions. Determine how particles attract, repel, or transform. Tweak them slightly, and the universe falls apart. If the strong force were weaker, protons wouldn't exist. If electromagnetism were stronger, chemistry would disintegrate. Then there's the Higgs field vacuum expectation value, how much it tilts in its lowest energy state. This value sets the mass scale for all particles. But why does the Higgs field tilt just enough to give electrons the right mass, without making photons heavy? Mixing angles describe how particles change identity under weak interactions, like neutrinos switching flavors as they travel. It's as if someone could change passports when crossing borders. The mechanism works but feels eerie. All these parameters let the standard model make stunningly accurate predictions. matching experiments to 10 decimal places or more. It's like a piano staying perfectly tuned through a storm. But where does this tuning come from? One answer: no reason. The values just are. The universe just is. An electron's mass is 0.511 MeV. Accepted. Most physicists aren't satisfied with that. We want to know why. We want a theory that predicts these numbers from first principles. That's what grand unified theories, guts, and string theory attempt, trying to go beyond the standard model, using deeper mathematical structures to reduce free parameters and link seemingly independent values. So far, no GUT has fully succeeded. String theory even suggests a more unsettling possibility: a landscape of countless possible universes, each with different parameter values. In some, electrons are too heavy for atoms to form. In others, stars never ignite. Our universe is just one where conditions happen to allow life. This is the anthropic principle. Instead of asking why the knobs are set this way, ask why their settings permit life. But this feels like giving up. A cosmic selection bias, not a deep answer. Many feel there must be a higher theory, explaining why the universe is finely tuned. Our exploration continues with the concept of running constants. Some physical constants aren't fixed, but change with energy scale. For instance, electromagnetic strength grows as particles get closer. At high enough energies, all forces might unify into one. The core idea of grand unification, though experiments haven't yet confirmed it. The fine-tuning problem is another mystery. Slight changes in parameters, like the neutron-proton mass difference, would prevent complex chemistry, star formation, and us. Is this coincidence or a clue? Neutrinos, extremely light, millions of times lighter than electrons, might get mass from a different mechanism than other particles. If true, the standard model is incomplete. String theory even proposes moduli fields, variables in the early universe that could have locked in today's constants. But so far, these remain theoretical, unverified. Now let's meet a more mysterious number, the fine structure constant, a seemingly arbitrary yet governing rule of nature. In science, one number appears almost everywhere. In quantum physics, atomic structure, electromagnetism, equations describing light-matter interaction. It's not an integer nor simply derived, yet it sets the strength of electromagnetism, arguably the most important force in everything we see, feel, and depend on. This number is roughly 1/137. More precisely, 1/137.035999206. Physicists call it alpha, the fine structure constant. It's one of the universe's strangest, most mysterious constants. We know how to measure it, how it affects physics, but not why it has this value. Alpha is dimensionless, no units, not meters, seconds, or kilograms, just a pure number like pi or e. That's key. It means alpha is universal. Even aliens would use the same alpha, regardless of their units. What does it do? Alpha determines how strongly charges interact, how protons and electrons attract or repel. It affects how electrons move in atoms, jump between energy levels, emit or absorb light, and how close they orbit nuclei. Without alpha, chemistry wouldn't work, matter and light couldn't interact, and atomic structures would fall apart. In atomic physics, alpha causes fine splitting in hydrogen spectral lines, hence its name. In quantum electrodynamics, it appears in calculations of electron-photon exchange and vacuum interactions, some of physics' most precise predictions, like the electron's anomalous magnetic moment, dependo na chiaritli in alpha. Yet where does it come from? We don't know. Unlike pi from circle geometry, or the gravitational constant from mass-force relations, alpha isn't derived from deeper equations, not set by symmetry, not a simple ratio of other constants. It's just measured. We point instruments at reality and say, it looks like 1/137. This number has haunted scientists for over a century. Arthur Eddington was obsessed with alpha, convinced it stemmed from deep logical principles, a cosmic code key. He tried deriving it from pure math, but his theory didn't hold. Richard Feynman said, "It has been a mystery ever since it was discovered. All good theoretical physicists put this number up on their wall and worry about it, even today." Alpha is among science's most precisely measured values, known to about 1 part in 100 billion, yet its origin remains unknown. Some hope a future theory of everything will derive alpha from first principles, perhaps in string theory, quantum gravity, or deeper unification. But decades of effort haven't yielded an answer. Others speculate alpha might vary over time or space. If true, it could help trace its origin. Scientists have studied light from billion light-year distant quasars, looking for slight past variations. Some data hint at tiny changes, others show none. No conclusion yet. An anthropic view suggests, if alpha were slightly larger, atoms wouldn't be stable. If smaller, stellar fusion might fail. Life requires fine-tuned conditions, and we observe alpha simply because we live in a universe where it permits life. But that's description, not explanation. Alpha's mystery is part of a larger puzzle. Nature's fundamental constants seem arbitrary, yet dictate everything's behavior. Light speed, gravitational constant, Planck's constant, electron and quark masses, all hard to explain. But alpha uniquely links quantum theory, electromagnetism, and relativity, yet still refuses to reveal its origin. Is gravity geometry's built-in property? That was Einstein's great leap. In the early 20th century, gravity was seen as a mysterious action at a distance force. Like others, Newton mathematically described gravity in the 17th century, but admitted not understanding its essence. Gravity moved planets and dropped apples, but its root cause was unknown. In 1915, Einstein's general relativity redefined gravity. Not a force, but a consequence of spacetime shape. In this view, massive bodies don't pull each other, they bend reality's fabric, and other objects simply follow curved paths. This was a radical shift. Gravity became geometry's attribute, not a distant force. Imagine spacetime as a rubber sheet. Place a bowling ball in the center. It sinks. Roll a marble nearby. It curves toward the ball, not because of invisible pulling, but because its path is bent. That's Einstein's classic analogy. And it wasn't just imagery, it yielded testable predictions. Light bends near massive objects, clocks slow in strong gravity, space stretches near stars and black holes. For a century, experiments confirmed these. Then in 2015, LIGO directly detected gravitational waves from merging black holes, another perfect match to Einstein. So, is gravity fully explained? On macroscopic scales, general relativity works beautifully, explaining GPS time corrections, planetary orbits, cosmic expansion. But at quantum scales, things get messy. In general relativity, spacetime is smooth, continuous, shaped by mass energy, a classical view. Quantum physics sees a discrete, uncertain, random world. The two don't merge seamlessly. Applying quantum rules to gravity yields infinities, failed equations, physical absurdities. One of physics' greatest unsolved problems. How to describe gravity in quantum language. Some physicists think Einstein was largely right but incomplete. Gravity might emerge from deeper quantum structures, where spacetime isn't smooth but made of tiny discrete units, like pixels in a game or atoms in a crystal. In such models, the curvature we see is just the macroscopic result of countless micro-interactions. The rubber sheet isn't rubber, it's digital. Others propose gravity isn't geometric at all, but informational. In this view, spacetime arises from quantum entanglement networks, defining distance and geometry as byproducts of information sharing. Gravity becomes a manifestation of quantum information flow. This isn't baseless. Theories like AD/CFT duality, holographic gravity, and thermodynamic gravity suggest gravity could be a thermodynamic or entropic effect, not pure geometric deformation. Does that mean Einstein was wrong? Not entirely. Just as Newtonian mechanics still works on Earth scales, Einstein's theory still works on cosmic scales, but there may be boundaries. A next-level theory might explain how gravity works at reality's deepest level. If gravity truly is built into space, why this kind of space? Why 3 + 1 dimensions? Why does gravity behave this way? Why is it so much weaker than other forces? If it comes from a deeper mechanism, what's the source? These aren't just theoretical curiosities. They affect our understanding of black holes, the Big Bang, wormholes, and the universe's ultimate fate. If gravity is geometry, the universe is a dynamic shape evolving in time. If it's something else, space-time might be an illusion cast by deeper laws we haven't yet discovered, thermodynamic laws. At first glance, simple, understandable rules. Heat flows hot to cold, total energy stays constant, perpetual motion is impossible. But beneath these straightforward statements lies a deeper physics question. Are these laws fundamental cosmic rules, or just statistical outcomes of more complex behavior? Start with the most familiar, the second law. Entropy always increases. Simply put, systems spontaneously go from order to disorder. Ice melts, batteries die, buildings crumble. The universe inevitably heads toward chaos. Yet at microscopic scales, the laws governing particles, nuclei and fields, are time-symmetric. They don't care if time runs forward or backward. If you filmed particle interactions and played it backwards, the physics would still hold, the math still works. So why does entropy always increase in one direction? It's one of physics' strangest facts. Macroscopically, there's an irreversible arrow of time, but microscopically, everything is reversible. Some scientists argue the second law isn't a cosmic commandment, it's a statistical tendency. With enough components, the most probable outcome emerges. Like a deck of cards, only one arrangement is perfectly ordered, but trillions are disordered. Given enough time, disorder is almost certain. That's entropy. From this view, the second law isn't a mysterious cosmic principle. It's probability theory applied to messy systems. The universe isn't forced toward disorder, it's just overwhelmingly likely to go there. Such emergence appears elsewhere. Temperature. A single particle has no temperature, but billions moving together yield an average kinetic energy, temperature. Pressure, just the average effect of countless tiny collisions. Thus, perhaps thermodynamic laws, energy conservation, entropy increase, heat flow, aren't fundamental rules etched into cosmic stone, but large-scale emergent phenomena. Yet some physicists think the second law might be more fundamental than we imagine, perhaps more basic than time and space themselves. Entropy plays a central role in black hole physics. In the 1970s, Stephen Hawking found black holes aren't completely dark. They radiate energy, Hawking radiation. More importantly, he and Jacob Bekenstein discovered black holes have entropy, proportional to their event horizon's area, not volume. This hinted that all information falling into a black hole might be stored on its surface, not inside, leading to the famous holographic principle. The entire universe could be like a hologram, with physical information in a volume encoded on a lower dimensional boundary. At this theory's core is thermodynamics. Some now think gravity itself might be an emergent thermodynamic effect. In 2011, Eric Verlin proposed, gravity isn't a fundamental force at all, but an entropic force arising from information and entropy changes. In this model, objects move together, not because of a mysterious pull, but because such motion increases entropy. True, thermodynamics isn't just kitchen physics. It might be the universe's operating system, the engine giving birth to space-time and gravity. So which is it? Are Newton's laws, which tell apples how to fall, also telling thermodynamics how to govern the world? Is emergence just what happens when systems get big and complex? No easy answers, but these questions force us to rethink what a physical law even means. Must rules like light speed limits or charge conservation exist from the cosmos's first moment, or could they emerge only after the universe grew complex enough? That leads to another question. Early universe physics laws, were they the same as now? Imagine the first few seconds after the Big Bang. No stars, no galaxies, not even light or atoms. Just an extremely hot, seething sea of pure energy. Space and time were just forming. The physics laws we know today might not have existed then. This isn't science fiction. It's one of cosmology's deepest, most serious questions. Did physical laws gradually emerge over time? Were they completely different in the early universe? To understand, we must talk unification. Today's four forces, gravity, electromagnetism, strong, weak, likely weren't always separate. In the extreme heat post-Big Bang, they might have been a single, indistinguishable force. As the universe expanded and cooled, this unity fractured, like metal cracking as it cools. Gravity may have separated first, around the Planck time, 10 superscript 3 seconds. Then around 10 superscript 3 seconds, the strong force split off. Later, the electroweak force, unified weak and electromagnetic, split into two. This process, spontaneous symmetry breaking, is a key idea in particle physics. If today's forces are broken symmetry products, the laws governing them must have been different early on. Equations describing gravity or electromagnetism today wouldn't have applied then. They took their current form after symmetry breaking events. Not just forces. Physical constants might not have been fixed either. Light speed, gravitational strength, particle masses might have been changing. Some theories even suggest constants, like the fine structure constant or gravitational constant, might have frozen as the universe cooled. A classic example, grand unified theories. Here, strong, weak, and electromagnetic forces are different facets of one force, described by a grand symmetry group. This symmetry only holds at extremely high energies, far beyond anything our labs can produce. Below a threshold, symmetry breaks, and today's three forces emerge. The early universe might have undergone phase transitions, like water freezing, where space itself suddenly changed structure. These transitions could leave relics, topological defects, exotic particles, maybe even explain why matter exists. Inflation, a brief period of exponential expansion, is tied to such a phase transition. During inflation, space expanded faster than light, smoothing and flattening the universe, possibly separating fundamental forces and locking in some key constants. Consider the Higgs field. Today it gives particles mass, but before symmetry breaking, its value was zero. All particles were massless, equations were different. Only when the Higgs field settled into a non-zero value did particles gain mass. Physics laws morphed from one form to another. Why does this matter billions of years later? Because it reminds us that seemingly universal, unchanging constants might be products of special early universe conditions, like today's landscapes shaped by ancient ice ages. It also opens a bolder idea. What if other regions of the cosmos, or even different universes, have completely different physical laws? In multiverse hypotheses, different space-time bubbles might have undergone different symmetry breaking, some with more forces, some with none, some without familiar space or time at all. Then our physical laws aren't cosmic bedrock, they're environmental outcomes. Even if we can't reach those regions, we might glimpse early universe secrets through cosmic microwave background radiation, the Big Bang's afterglow. Tiny fluctuations in this radiation might preserve imprints of early phase transitions. Analyzing them, maybe one day will confirm whether cosmic laws evolved over time. Perhaps cosmic rules aren't eternal truths carved in stone, but temporary answers floating in time's river. When new laws emerge and old truths crumble, we'll discover that what we held as unchanging principles were just footnotes in a grander script. So the real mystery isn't why the universe follows rules, but who or what decides when the rules should change. When that moment comes, even the language we use to ask questions might be redefined. Alright, my friend, let's pause our conversation here tonight on the mysteries of the universe. Now allow me to press pause for you. Set aside all thoughts and inquiries and simply, quietly, be in this moment. From here, my voice will fade away, leaving only the silent tapestry of the cosmos and a carefully chosen piece of pure music tuned to 432 Hz. Science suggests this frequency resonates deeply with the natural vibrations of the universe and the rhythm of life itself, soothing your nervous system and guiding you into deep relaxation. Now, find your most comfortable position. Gently close your eyes or let your gaze rest softly upon the stars. May you release all weariness from the world, letting your consciousness drift on the waves of music, floating into boundless tranquility. Good night, sweet dreams, until we meet again among the stars.